Welcome to another explainer. Today, we're going to dive into the absolutely mind-bending reality of why water, something we all interact with literally every single day, totally breaks the fundamental rules of the universe. And honestly, it's a good thing it does, because this weird little anomaly is exactly what supports all aquatic life on Earth. Most of us take water completely for granted, But its physical properties are actually wonderfully, wonderfully strange. Okay, here's our roadmap for today. We're going to start with the universal exception of floating ice, explore hexagons and hydrogen bonds, and then unpack the 4-degree mystery. After that, we'll look at simulating network collapse, check out a very rare club of expanding materials, and finally, we'll see exactly why ice saves life. Section 1. The ultimate universal exception, breaking the rules of freezing. So, let's start with a super common, everyday observation that is actually incredibly profound once you really stop and think about it. Think about it. If you drop an ice cube into a glass of water, you're literally witnessing a phenomenon that defies the standard behavior of matter. You see, the general rule of thumb in the universe is that when things get cold, they pack tightly together, right? Gases condense into liquids, and then those liquids freeze into really dense, heavy solids. But water? Well, water just completely plays by its own rules. While nearly all normal substances shrink and get denser as they freeze, meaning their solid form will just sink right to the bottom of their liquid form, water actually expands. As it freezes into ice, its volume increases by about 8.1%, making it roughly 9% less dense than its liquid form. And that right there is exactly why your ice cubes are bobbing at the top of your glass instead of sinking to the bottom. Section 2. Hexagons and hydrogen bonds, the microscopic architecture. To really understand why this happens, we need to zoom way, way down into the microscopic architecture of water and see what these molecules are actually up to. So a water molecule, H2O, is shaped kind of like a V, with an angle of about 105 degrees between its 2 hydrogen atoms and 1 oxygen atom. Now, as liquid water cools down, the molecules start to slow their chaotic tumbling. And this slowdown allows these special forces called hydrogen bonds to kind of take over. These bonds form between the positively charged hydrogen of one molecule and the negatively charged oxygen of its neighbor. Think of them acting almost like structural struts, holding the molecules at very, very specific distances from each other. And the geometry at play here is just fascinating. Each oxygen atom is surrounded by 4 hydrogen atoms in this neat little tetrahedral shape. 2 are covalently bonded to the oxygen, and 2 are held by those hydrogen bonds we just talked about. It's this exact, very particular spacing that completely prevents the molecules from squishing any closer together. And because of that precise tetrahedral spacing, the freezing water is essentially forced to form a rigid, open, hexagonal crystal lattice. Just imagine a highly organized scaffold. Now, because of this strict structural requirement, the resulting ice lattice is actually full of microscopic empty space. They're essentially tiny vacuum channels. The molecules are literally forced to push apart to maintain this crystal structure, which means they end up taking up way more space as a solid than they ever did as a tumbling liquid. Section 3. The 4-degree mystery, a classical physics puzzle. But hey, water's weirdness doesn't just stop at freezing. Oh no, it actually behaves strangest right before it turns into ice. Get this, water actually reaches its absolute maximum density at exactly 4 degrees Celsius. This specific, super weird temperature anomaly baffled scientists for decades. Even great minds like Bernal and Fowler tried to model this way back in 1933. They proposed that water was basically a mixture of ordered ice-like structures and disordered, dense liquid structures. If we map out the macroscopic density curve, you can see the peak sitting exactly at 4 degrees Celsius. Now, as the temperature rises from 0 to 4 degrees, you would normally expect a liquid to expand, right? That's just standard physics. But here, the density actually goes up. So why does it do that? Well, it's because the incoming thermal energy is breaking those rigid hydrogen bonds we just talked about. So following this sequence, as ice melts at 0 degrees, some of that rigid structural scaffolding just collapses. Those disconnected water molecules slip right into those empty vacuum channels in the hexagonal lattice. And here's the really cool part. Between 0 and 4 degrees, the rate at which those molecules are filling up the empty space actually outpaces the normal expansion caused by the heat. It's only once we pass 4 degrees that the thermal velocity of the molecules is finally strong enough to push them apart. So past 4 degrees, it finally starts behaving like a normal liquid, decreasing in density as it gets hotter.
Section 4. Simulating the network collapse, a machine learning breakthrough. For decades, this whole mixture of ordered and disordered states was just a really great theory. But to truly map this mechanism at the atomic level, modern physicists had to deploy some seriously cutting-edge tools.
The big challenge here is that running quantum mechanical simulations of water is just incredibly complex and wildly computationally expensive. So to solve this, researchers at Temple and Princeton universities brought in deep neural networks. They trained these AI models on advanced quantum mechanics data, specifically density functional theory, which created something called a machine-learned potential. And this was a massive breakthrough because it allowed them to simulate the exact interactions of water molecules at a huge scale with just staggering accuracy. This whole dynamic is perfectly captured using a really neat geometric tool called Voronoi cells, which basically maps the local volume of each molecule. In these mapped snapshots of liquid water, the blue areas represent regions of high local density, while those orange areas show low local density. It's so cool because it visually proves what was hypothesized for nearly a century. Liquid water is actually an incredibly dynamic, heterogeneous mixture of all these different local structures that are just rapidly shifting around. But the simulation revealed something even more specific than that. It actually proved that the immediate short-range tetrahedral bonds around a water molecule remain mostly intact even in the liquid state. So the real driver of the density anomaly, it's the collapse of the intermediate scaffolding, or what physicists call the second coordination shell. It's the breaking down of this wider network that allows the molecules to slip into the gaps, creating those high-density blue zones we just explored. Section 5, a very rare club, other expanding materials. Now, while water is definitely the most famous example of this phenomenon, mostly because it's literally everywhere, it is not entirely alone in the universe. When we look at the data, we can actually see water's rare company. Elements like silicon, bismuth, and gallium also share this incredibly unusual trait of expanding when freezing. I mean, look at silicon. It expands by 10% when it freezes, and it does that at over 1400 degrees Celsius. Crazy, right? But what all these materials have in common is that they're network-forming materials. They rely on open, tetrahedral-like crystalline structures when they turn solid, which forces their atoms into these spacious arrangements, exactly like water's hexagonal lattice. Section 6. Why ice saves life. The macroecological impact. So let's zoom all the way back out from the quantum physics and the crystal lattices to the macro scale, and let's just look at our own planet. Why does this tiny microscopic quirk matter so much to us? Well, because ice is less dense than water, lakes and oceans freeze from the top down. When a harsh cold snap hits, clear, really strong black ice forms first right on the surface of the lake. And this layer of ice essentially acts like a massive thermal blanket. It just sits there, right between the freezing winter air above and the liquid water below, totally preventing the rest of the lake from losing all its heat. This whole temperature anomaly sets up an absolutely perfect environment for survival. Since water is densest at precisely 4 degrees Celsius, that relatively warm 4-degree water naturally sinks all the way down to the very bottom of the lake. Meanwhile, the lighter, colder water and the solid ice just stay floating on top. And this creates an incredibly stable liquid refuge down at the bottom. Fish and all sorts of other aquatic organisms retreat to this deep zone. They enter a slow metabolism state called torpor, and they're completely protected beneath the ice all winter long. Which honestly leaves us with a pretty profound realization. Just think about it. If water behaved normally, if the solid form was denser and actually sank, the ice formed on the surface would constantly fall straight to the ocean floor. Eventually, our lakes, our rivers, and our oceans would just freeze entirely solid from the bottom up. Every single winter, aquatic life would be totally eradicated. So the microscopic geometry of a single hydrogen bond is quite literally the foundation that allows life on Earth to persist. So the very next time you drop an ice cube into your drink, ask yourself, what other hidden miracles of physics are just hiding in plain sight?